Hey guys, welcome to our Unit 5 Momentum, and this is going to be where we start talking about our egg drop projects also. Momentum is a really interesting idea. It's the thing that kind of bridges the gap between kinematics and dynamics in a way that energy did also. So let's start taking a look at stuff. So Newton's first law states that an object remains in motion with a constant velocity unless acted upon by a force, that external force. So in everyday life, we kind of see this thing when two objects of different masses travel with the same speed, the one with more mass is harder to stop. And we understand that running into larger things, right? When objects of equal masses travel with different speeds, typically the faster one is harder to stop. So the idea of momentum, p, lowercase p, is defined to account for these observations. Momentum is mass times velocity. We use lowercase p, m for mass, and v for velocity. So the momentum of a single object is the product of its mass and velocity. Momentum, like force and acceleration and velocity, is a vector. The unit for momentum is the product of the units, so it's just a kilogram meters per second. We don't have a special name for it. A quick example, the momentum of a 3,000 kilogram truck traveling at 15 meters per second. So here's our givens. And then this first example is pretty straightforward. We just plug everything in to get 45,000 kilogram meters per second squared. Or I'm sorry, just per second. So that one's just straight plug and chug. Second example, we have a boat that has a certain mass and a momentum. We're looking for the velocity. So first steps, write our givens down, make sure we know where we're going with this. And then on this one, we see that the momentum is given and the mass is given, solving for velocity. So just making sure we understand which one goes where. Then another one, a car given the velocity and the momentum, solving for mass on this one. So P equals mv, m equals P over v. Notice the units end up canceling out, leaving just the kilograms. So there you go. So that was a pretty straightforward solving for momentum. A more interesting concept or idea is the momentum of a system of objects. So if a system contains more than one object, the total momentum is the vector sum of the momenta of those objects. So we have the momentum of the system is equal to the sum of momenta. So what that looks like is momentum of the system, P is P1 plus P2 plus P3, so whatever objects and masses that we have. And then when we substitute the MVs for Ps, we have M1 V1, M2 V2, so on and so forth, just indicating the different masses and velocities of objects within a system. So, whoops, duplicate slide there. So when we talk about the momentum of a system of objects, there's our big main equation. Remember the dot, dot, dot just means I could have, multiple things there. So to determine the total momentum, we have to choose a direction to be positive. Assign positive values to the momenta in that direction, and then everything going opposite direction has negative values. And then we add the momentum or the momenta to get the total momentum of the system. So an example of that looks like this. We have two objects, M1 with a mass of 6 kilograms and a velocity of 13 towards the east. That part is important. And M2 has 14 kilograms and a velocity of 7 meters per second to the west. So these are going in opposite directions. So when I write my givens out, notice I have my V1 as positive 13 and my V2 as negative 7. That takes care of which way those are going. When I plug things into the big equation, I have M1, V1, M2, V2. And so when I plug everything, I get the 6 times 13, that gives me the positive, but the 14 times negative 7 gives me the negative. When I add those up, I end up getting a net negative 20 kilogram meters per second for the total momentum of the system. So the total momentum of the system is 20 kilogram meters per second to the west or in the negative direction. So that's great. We figured out how to calculate momentum and we see what that looks like. But like we talked about in energy, sometimes the change is more important. So suppose there's an event that changes an object's momentum. We have the initial momentum P naught just before the event, and then delta P is the change. That's the change in momentum, of course. And the final momentum is just after the event. So the equation for the change of momentum, it looks kind of interesting, but the initial velocity or the initial momentum plus the change is equal to the final. And so we can rearrange that in several ways depending on what the question is looking for. So this ties up into Newton's first law, kind of nice. Remember, it's going to keep doing what it's doing unless it's affected by an external force. So we define impulse I, that should be a capital I, as the external force acting on the object for a certain amount of time, or I equals F delta T. This is called the impulse. So the impulse changes the momentum of the object. So we have I equals delta P, PF minus P naught. So putting those expressions together results in the impulse momentum equation, I equals F delta T, which can be expressed as I equals delta P, PF minus P naught. So depending on where, what kind of question is asked of us, it changes what order those things go in. So that's just kind of nice to be able to use that. So there's no specialty named unit for impulse. We just use the product of force times time, which is a Newton second or a kilogram meter per second. So all the same unit for momentum. We don't have a specially named unit for that. So one of the interesting things that we'll be talking about is the effect of collision time on the force. So if you look at my little equation here, for any given impulse, the greater the force means the smaller the time, or the smaller force means an increase in the amount of time the object is impacted for. So since force is inversely proportional to delta T, changing the delta T of a given impulse by a small amount can greatly change the force exerted on the impact. So at this point, we're going to just work with magnitudes, and we're going to drop the vector sign in all of our equations, which kind of just helps us write stuff out a little easier. So the inverse relationship of force and time interval leads to interesting applications. We have structural safety design in cars, airbags, landing after parachute, hitting and catching baseballs. All of those things can be analyzed using this impulse, force, and delta time. So let's take a look at an airbag. So whenever you have an equation with 3 variables, we have to decide which value will be fixed, which will be varied to determine the impact on the third value. So in this case, we're going to fix the delta P, or the impulse, and vary the T value to see its impact on the force F. In dynamics, we talked about how seat belts protect passengers from the effect of Newton's first law by stopping the passenger with the car and preventing them from hitting the dashboard or being ejected from the car. They also provide another benefit explained by the impulse momentum equation, but we can see this a lot more easily with the presence of airbags. So the seatbelt slows down, increases the time interval that it takes the passenger to slow down. There's some play in the seatbelt that allows you to move forward a bit before it stops you. The airbag, when it deploys, will increase that time interval much more than the seatbelt by rapidly expanding, letting the passenger strike it, and then deflating. And so basically what it's doing is, instead of stopping very quickly, that is a huge force exerted on the person, what that time does, if it increases the amount of time, the force gets small, or the person experiences a smaller force based on the amount of time it took to stop. And that's kind of why these things were developed. So we have an example question that it takes care of a lot of these things here. So we have 3 questions here, and so I did it based question by question for slides. So we have a constant force of 12 newtons for 5 seconds acting on a 5 kilogram object. The first question is the impulse delivered. So given the force, the time, the mass. So I is just force times time, 12 times 5, giving me 60 Newton seconds. That's what the impulse is. Oh, there it is right there. So the next question is the change in momentum. And so if we remember, the change in momentum is equal to the impulse. So this is the same thing. You'll notice a lot of these questions will ask the same kind of question. And based on our knowledge conceptually, we should be able to answer some of them fairly quickly. And then the object's change in velocity, we'll have to go back and look at the I equals delta P, so M1 V1 minus M2 V2, and we'll have to figure out what that delta V is, and we'll do that when we come into class next. All right, thanks for watching. I'll catch you guys later. Bye.